Hot water, particularly in astro programs, is required.
Let's go over tomorrow on Friday, maybe just, some of the plots you've already given me, fine. But the transport will be useful. Not what I want.
I had a talk with Nashki Beignet, you know who I am.
How you feeling? Been better. Okay.
Well, you know who I am.
Well, pretty far work.
Very
Very
I'll manage the questions, yeah. So do you want to use the green is top is laser, left, right? You'll push that, screen will go blank, you'll freak out for a second.
I gave a talk at the conference, and
It's already happened to you.
oh yeah, it was because I think it was swapped. Like
Oh, okay.
And I just kidding, and like every 5 slides,
I can't imagine any time.
Yeah. Okay, all right. You're attuned.
I can calm myself down. So the usual 5 minutes after.
Yeah, and I don't think my hair stands, so that's right now. Great, well, yeah, sorry. But Adam and George are probably getting it, so. Okay, so we're really excited to have Paul Sutter here today. Paul is a graduate student at University of Illinois at Urbana-Champaign, where he worked on various things, but AGN feedback clusters, I think.
Yep.
And since then, he's supposedly been in Paris at the IOA, and I just want the grad students and postdocs to listen to this story. He is paid by people in Paris. He is supposed to be in Paris, and he actually lives at Ohio State University. So it is possible to get paid and technically be a postdoc in an institution and literally live in a different continent. In case anybody needs something like that in the future, it can actually be done.
However, you
So
can't
if you're
return to
dreaming-
France anymore.
No, is there every
If you're
Yeah,
dreaming
yeah,
to live in Ohio State.
Actually,
Many of us would rather be paid by Ohio State than live in Paris.
Actually, a postdoc salary goes much, much farther in the Midwest than it goes in downtown Paris.
But I think it turns out there's more flexibility in some jobs than maybe in parent companies. And then Paul this fall is going to start with a new postdoctoral position in Italy, where he will continue to reside at Ohio State. And at Ohio State, he's been working with David Weinberg on various issues, and he's been working for a while now on voids, which he's going to talk about today. But I wanted to also mention that he's also part of the Planck team. I think you've been working on non-Gaussianity on Planck data. So especially at the end, if anybody has any other questions about Planck or AGN feedback and clusters, we can ask those as well. But today we're going to hear about voids.
All right, thank you very much for having me. I'm going to talk about voids, cosmic voids, which, as the name suggests, are the large empty places in the large-scale distribution of matter in our universe. And these voids start out, like everything else, as tiny density perturbations. And as structure forms, as matter collapses to form sheets and then filaments and then clusters, it leaves behind these evacuated regions that we call the voids. So the properties of these voids, their sizes, their shapes, their density profiles, velocity profiles, or whatever, their properties must be sensitive to cosmology. Because it's just another way of slicing the cosmic web. Instead of looking at the growth of structure, we're looking at the growth of not structure. If you change cosmology, you change the growth of structure in our universe, and you change the properties of voids. So they must be cosmological probes. But it turns out these voids are actually very special places in our universe. They have some special properties that we can take advantage of. First off, they probe a useful set of scales from 10 to 100 megaparsec, which are not usually probed by traditional cosmological probes. And because they're empty, by definition, they've been dominated by dark energy for longer than the background universe. So if you're interested in the history of dark energy, or exotic dark energy models, clustered dark energy, coupled dark energy, fifth forces, whatever, they'll be stronger, relatively stronger inside of a void because they're made up of dark energy. And they haven't changed much since the very early universe. They're still in the linear or quasi-linear regime. So this means they provide a window into early universe physics. They still retain a memory of the primordial initial conditions. It hasn't been corrupted or swamped by nonlinearities. And this linear, quasi-linear behavior means that any systematics, due to, say, peculiar motions of galaxies, which might contaminate that cosmological signal that you're trying to get, are going to be easy to model and easy to remove. And I'll show examples of all this later. And finally, voids are abundant. They literally fill up the universe. Most of the universe by volume is inside of a void. So if you want a volume-weighted test of cosmology, voids are the things you're going to use. The basic idea that we try to get across with voids is that they're a way of accessing higher order statistical information in the cosmic web without having to deal with large systematics. And with that idea, with that nugget of wisdom, you can start thinking of ways to use voids as a cosmological probe, ways to extract their properties and tie them to cosmological parameters or physical processes. And voids have become very popular. There's been an explosion of interest over the past few years in voids of all groups all over the world, thinking of ways to use voids for cosmology and for astrophysics. I'm going to return to this list later in the talk and highlight some of these projects in more detail. But first, I need to lay some groundwork. Some groundwork like, well, how exactly do you find a void? It's easy enough by eye to take a galaxy survey or an n-body simulation and, oh, there's a hole there, there's a hole there, there's a hole there. And so you could just pay a bunch of undergrads to go around drawing circles on galaxy surveys. You can do it in 2D. It's a little bit harder in 3 dimensions. So we need to teach a computer how to do it. And we have a 2-step algorithm that we call VID for void identification and examination. It's the French word for empty. That's where it comes from. VID has been in development for the past couple years, and starting tomorrow, it will be publicly available. The entire algorithm, open source. The paper will appear on the archive tomorrow, and I'll tell you a link and all that later in the talk. But VID has 2 steps. The first step is to construct what's called a Voronoi tessellation. So let's say you have some set of particles. These could be galaxies in a survey. They could be dark matter particles in a simulation. It doesn't matter. We're just going to assume that they trace an underlying density. Now we'll pick one particle at random, and we'll go to its nearest neighbor. And we'll draw a line at the midpoint between that particle and its nearest neighbor. So in 3 dimensions, this would be a plane. Then we'll go to the next nearest neighbor and draw a line or a plane there. In the next nearest neighbor, in the next nearest neighbor, the next, on and on and on until that particle is completely enclosed by a set of planes, a bunch of facets. And we'll repeat this for every single particle or every single galaxy. This gives us a tessellation. A tessellation is a set of geometric figures that completely cover a space with no gaps and no overlap. That's the definition of a tessellation. And this Voronoi tessellation has some very unique properties that we're going to take advantage of. You'll notice that where particles or galaxies are close together, these Voronoi cells, the little local tessellation area, are relatively small. In places where the particles are far away from each other, the Voronoi cells are rather big. So the Voronoi tessellation gives us a map of the local volume of each particle. In fact, topologically, it's the only definition of a local volume of a particle. It is the Voronoi volume. And you can invert these volumes to get a density. So the Voronoi tessellation gives us a map of the density field from a set of tracers. And these tracers are galaxies or dark matter particles or whatever. This Voronoi tessellation is the underlying density field. That's step one.
Is it unique?
Yes, this Voronoi tessellation, there's only one Voronoi tessellation for this set of particles. Now, that's step one. Step two, imagine you have this density field. And imagine it's like a topographical surface. There's high density mountains and plateaus and ridges, and there's low density basins and valleys. Now imagine taking this density map and sprinkling water on top of it, just like rain drops on top of a geographic surface. The water will naturally collect into the deep valleys. That's where it falls. It falls into the basins. So in one dimension, the raindrops will collect in these basins, and there'll be places which split the flow of water. We call these ridge lines. If you sprinkle drops of rain onto the Rocky Mountains, some water will end up in the Pacific, and some water will end up in the Atlantic. It's a ridge line. It splits the flow of water. And this area is called a watershed. A watershed is a basin that's surrounded by a common set of ridge lines. And so this is how we're going to topologically identify a void. We're going to call a basin a void. The high density parts in our cosmic web are clusters and filaments and walls. They separate these basins, these low density basins. So in this picture, a void, what we're calling a void, is just a low density basin in the density field of the universe. That's all it is. And this gives us an enormous amount of flexibility. Because the tessellation is unique, and because this watershed segmentation of the volume is unique, we can apply this algorithm to galaxy surveys. We can apply them to n-body simulations. It doesn't matter. It's all topologically identified, and there are no parameters. There's nothing to tweak. There's nothing to adjust. The tessellation is the tessellation. The watersheds are the watershed. That's it. And this watershed approach allows us to uncover a hierarchy of voids. Just like there's hierarchy of structure in our universe, galaxies, groups, and clusters, there are voids and subvoids and sub-subvoids and sub-sub-sub-sub-sub-subvoids, and on and on. There's hierarchies of structure. And as the watershed operates, as we start from the deepest basins and cover up ridgelines, we're able to discover two adjacent voids, might have a low density filament or wall between them, and they're part of a larger basin, a larger void. So we're able to extract all the void information at all scales in a galaxy survey or a simulation. We can get the biggest voids, and we can get the smallest
So the
voids.
void map is a function of the height of the water, in a sense? I mean, you get many different void maps depending on where you set the water level?
So the water level starts at the bottom and goes all the way up to the top. So in this one-dimensional picture, you might get one void here that has some minimum density and some mean density. and you'll get another void here that has a lower minimum density and maybe a different mean density. And as you fill up, now there's a parent void here, there's a
I
larger...
guess I'm just saying that the number of voids in the sides depends on the water level.
Yeah.
Right?
So
It goes all
it goes all the way to the top, so you have a full hierarchy. So if you pick out one level in the hierarchy, say one density threshold, you'll get a certain volume distribution of voids, number distribution of
I
voids.
guess I'm just asking, when you say a void, that's not enough to identify a void. You have to know something else, which is that it's water level of some.
Nope. All I'm going to pick out are all the basins in this density field. That's it. Every divot, every bowl is going to be a void.
I think it as a function of how far you fill in, right? So as you fill all the way to the top, you'll get one void.
At the very, very top, there is one void that encompasses the entire universe.
And that,
In this watershed approach, okay, it has mean density equal to the mean density of the universe. Okay. Below that, you start segmenting the volume until you get to the very tiniest segmentation.
Is there a critical level below the top level where you hit a percolation threshold? You basically, in other words, it's obvious at the top level you'll fill the whole space, but I mean, suppose, it seems to me you could go below that, right? It would set a kind of percolation threshold.
Yeah,
And
so
that would characterize the terrain at some level.
yeah, you're absolutely right. And what's typically done, this watershed approach, you can operate it in a fully parameter-free mode, or you can introduce some thresholding parameters. Like if there's two voids next to each other, here's a void and here's a void, I can examine the ridge line between them. And I can ask about if this density between them is too high, say greater than 0.2 times the mean density. If that's too high, then I won't join these two voids together. I won't agglomerate them into a larger parent void. And that does give you a density-based natural kind of percolation segmentation of the volume. But we like to operate in a full parameter-free mode because no reason really, because it's fun, I guess. So we uncover the full hierarchy of voids, and here's what a typical void looks like. This is in a galaxy survey. This is real data. This is in the SDSS main sample. You're looking at a 20 megaparsec void, and you can see this complex, multifaceted structure of all these little Voronoi cells that have been glued together because they all share a common basin, and they're all bounded by these high-density ridge lines, by these galaxies that bound it in 3 dimensions.
I have to keep coming back to this. I still haven't got it. I didn't think. If you set a different water level, that would be a smaller void or a bigger void. So you must specify what the water level is to decide, make that purple.
Okay, I think I understand the source of your question. This picture that I was painting where we start at the bottom and fill to the top, algorithmically, it actually, all hierarchies are discovered simultaneously. So if I go over here, it doesn't matter if, for presentation purposes, I was saying, the water level starts off here, but this is a void, and this is a void simultaneously in the algorithm.
Now, when you plot the purple thing, do you have it the size of the first one or the size of both of them? That's what I don't know.
Oh, this parent? This, so there's like
two voids
parent
here
void?
that you could show a purple thing for, and when you show the purple structure, I don't know, you must specify whether you're.
Yeah, I have to specify where that void is in the hierarchy, because this purple void,
Yeah.
it could absolutely have some, say, low-density filament inside of it that further segments it into 2 volumes. Just like if I showed you a picture of a halo,
Yeah.
it could have subhalos inside of it. So this particular void, I have no idea if it has subvoids. I didn't check when I made the plots. But it absolutely could. But for purposes, for all the cosmological results that I'm going to show, either we take all voids in the full hierarchy, or we pick out just what we call top-level parent voids, which would be just this super void. And in our public void finding algorithm, we have all sorts of filters built in, so you can pick out just the deepest children, just the parents, the full hierarchy, whatever you want. It depends on the application and what you're trying to go for.
Is there any scaling rule with the number of voids versus fine grain kind of? It looks like this algorithm of determination of topological dimension of space, like Hausdorff dimensionality. Is any relation to this procedure?
Yes, there's been some work, especially on genus statistics, and I don't know if there's been any specific work on the relationship between a watershed segmentation and a general classification of cosmic web structures based on, say, velocities or geometrical statistics. There is a connection there because what we're doing with watersheds is picking out chunks of the volume. And so that has to be related to deeper geometrical structures. This is just another way of approaching it. But there hasn't been, I don't think, a really detailed analysis look at that. I'm sure some mathematicians 150 years ago.
No relation to fractals.
Yeah. Is the void hierarchy self-similar?
That is like 3 or 4 slides worth of my talk.
If the answer is yes, then there must be a relation to fractal dimension, as Misha is saying, and the question is what's the
What number?
What is the fractal dimension?
What's the effective dimension of
Okay.
occupation?
So I was going to bring up fractals, but you said it, so I'll talk about it.
You said the F word.
You said the F word. I've made that joke. Yes, voids are self-similar, and I'll show some beautiful examples of that in a little bit. And so they are fractal, and they're fractal because the voids exist in the region of the power spectrum where it's k to the minus 3. Right? It's before turnover and after nonlinearity. That's exactly where voids live. And so you have a uniform power spectrum that gives you self-similar structures. Now you can ask, what is the fractal dimension? There has been some work on this, especially in the mid-90s. I think there was work. It turns out voids are fractal, but in a very non-trivial way. And the best phrase I found to describe it was that voids are
Multifractal.
non-lacunar multifractals. So they can't be described by a single fractal dimension. But there is self-similar structures arising, and I'll show examples of that. They are there, but they're hard to describe by simple fractal.
Okay, so the question, if you go to multifractals, then you start to look at what amounts to higher order moments of the void distribution. Right? I mean, if you go to multifractals, that's where you have to go to reveal the multifractality.
Mm-hmm. You're absolutely right. So that's...
I didn't know this was plasma physics.
You should take my estimation. Hans.
So there's a void. That's just one void. It's not alone in galaxy surveys. It has over 2,000 friends, and you can go visit them at cosmicvoids.net. It's a public catalog of all of our voids identified in redshift surveys, and not just that. It's voids identified in mock galaxy surveys. It's voids identified in n-body simulations, and there's even more. Starting tomorrow, there'll be the void finding algorithm feed itself, and not just the actual code for finding voids, but all of our analysis toolkit that we've used. So pretty much all the plots that I'm about to show you for all of our science results, you can do yourself on your own void catalog that you identify in a redshift survey or in a simulation. It's all there, supported as best we can support it, and publicly available. We only ask for a citation.
I have a low-level question.
Yeah.
I mean, you started making these points, but when things get far away, they get fainter.
Mm-hmm.
So your points will be less often, and the size of your voids will therefore change with distance, right?
That's absolutely
How are
right.
you correct for that?
What about sparsity of tracers and galaxy bias? You're right.
Right, thank you.
This is absolutely right. You run a galaxy survey. Things are fainter, harder to detect farther away. You can only see the bright stuff. So your tracers of the cosmic web itself, you don't get the full say, dark matter filament. You only get a skeleton of it. And so the thing that you're going to identify as a void with this watershed image volume segmentation is going to change. So what about the fact that galaxies are sparse, they're biased? What about things like peculiar velocity, survey mass? What about dynamics? Voids do evolve. All of these could impact your cosmological signal or your understanding of what a fundamental void is. So I'll start with sparsity and bias. And to examine this, we ran a high-resolution n-body simulation. So this gives us what the dark matter is doing. We identified voids in this dark matter distribution. Then we painted galaxies onto the dark matter using a halo occupation distribution modeling. So it's tuned to a particular survey. So we get a galaxy population that at the 2-point statistics level looks like a particular galaxy survey. And then we found voids in that mock galaxy population, and we compared them. So here's a slice in the dark matter, and you can see the cosmic web. There's an empty-ish region there. There's a basin in the density field. And here in red is a circle representing a void found in the dark matter. And I'm not very good at drawing voids, so you're just going to get circles. So there's the void in the dark matter, and then this yellow circle represents the void identified in the galaxies. It looks bigger. It looks different. You've replaced this nice, broad filament of dark matter with just a tiny, thin skeleton of galaxies. So the object you pick out looks inflated. Your sense of where the center is different because there's all sorts of dark matter substructure that doesn't light up with galaxies. So your best estimate of where the deepest underdensity is going to change. So initially, this looks completely different. Voids in dark matter look different than voids in galaxies. They have different size distributions. They have different density profiles. Here's the density profile. And they share a common general shape, completely empty in the center, a very steep wall when you run into the nearest filament or sheet or cluster, a slightly overdense bump known as the compensation region. This is from the pileup of matter as it outflows from the void, and then it asymptotes down to the mean density. But here, this in red, or sorry, yeah, in red is the density profile in the galaxies, and in light blue is the density profile in the dark matter. There's more substructure in the dark matter than in the galaxies. But an interesting thing happens. If we recenter, if we put these voids on top of each other and then rescale the dark matter void, the density profiles look almost exactly the same. So that suggests that there is a connection between voids in the dark matter and voids in a galaxy survey, and voids at different scales. There's some sort of fractal, self-similar thing happening. And let me explore that in more detail. But in order to do that, we need a little bit of technology.
Well, wait a minute. Doesn't that depend on what you chose for your distribution of galaxies that you scattered on top?
Nope. And I'll show you. What do you? Okay.
Well, but in general, how much you rescale is going to depend on the density of your.
Yes. That's 2 slides away, maybe 3. But it's coming. Oh yeah. So this little bit of technology is a universal density profile. It's a 2-parameter functional fit to any density profile that we are able to throw at it. So just like the NFW profile for halos, this is a density profile for voids. And you're looking at different sizes, so 10 to 15 megaparsec, all the way up to 60 to 65 megaparsec, and then in the paper not plotted here, all the way up to 90 megaparsec voids. And these different colors are voids in different kinds of populations. So in red are voids in a high-resolution dark matter. Dotted red is low-resolution dark matter. Blue and green are voids in high-density galaxy mock surveys, low-density galaxy surveys, halo populations, high density, low density. So all sorts of many different void sizes and many different densities, underlying densities and biases of the tracer population. We find voids in all of them, and this single function with 2 free parameters is able to fit all of them just fine. And if you look at one void size, like 30 to 35 megaparsec, voids at this size, they look very different. Voids in, say, galaxies have these very tall compensation regions and very deep underdensities. The voids in the dark matter here, much shallower compensation regions, not quite zero density. They look different. They can all be fit and described by this single function. Yeah.
I can understand how one can measure for the galaxies that curve, but for the dark matter, how can you get it so accurately?
Oh, so this is all in simulation.
Oh.
Yeah, these are not observations, but there is a way of accessing the dark matter density inside of void in observations that I'll show at the end of the talk. This is all mocks, all simulations, all theoretical.
So you will show one of these plots with real data on it, so we believe these plots have anything to do with reality?
Almost. I'll show it. Actually, I won't show in this talk, but there's a recent paper by Bhuvnesh Jain and Joseph Clanvid where they're able to get constraints on these parameters using using something I'll talk about.
What's in the simulation?
Simulation is just pure n-body simulation with galaxies painted on it using halo occupation distribution modeling. So at first blush, they look all sorts of different. But if I take their fitting parameters as a function of void size for each of these different kinds of populations, here's one parameter, the central density, another parameter, the scaling radius. You have all these curves scattered all around, but it looks like I can do some rescaling. It looks like that if I say take a void in high resolution dark matter, say a 20 megaparsec void, well, it has the same central density as, say, a 45 megaparsec void in a sparse galaxy survey. And so if I pick some fiducial point, all these curves are clustering around what appears to be a common relationship. And this is exactly this fractal nature, this self-similar nature. Voids, different populations, galaxies, high resolution, low resolution, dark matter, whatever, are just picking out different regions in this void hierarchy. They're just picking out different scales. But because voids live in this self-similar region of the power spectrum, it allows us to do things like rescale. It's telling us that if we observe a population of voids in a galaxy survey of some density and some bias, that they are fundamentally connected by simple scalings to voids in the underlying dark matter. We don't yet know what that exact relationship is. We don't know for a given galaxy survey of a given density and bias how much we need to rescale. But this is giving us hints that such scaling relationships exist in the first place, and that now we can go start looking for them.
And that's not just a function of the simulations you've done and the forms of the way you've simulated things.
So we run an n-body simulation. It gives us a dark matter population. We put galaxies on top of it. It matches the 2-point statistics of a galaxy survey. So the power spectra between the simulation and the survey agree by construction. Given that, we're able to uncover these kind of properties.
And any missing baryonic physics would be on much smaller scales than this. I mean, this is all, that was one of the points, this is all in linear scales.
Linear or quasi-linear?
Bigger than 10 megaparsec.
Yeah, baryons, this is not, baryons in the form of galaxies are going to trace the cosmic web, which is how we identify them. But baryonic physics, They don't change density profiles. And this has been shown in ab initio simulations with gas. You get it's dark matter and it's dark energy dominated, and then what little stuff is left inside of a void is all dark matter. There are still baryons floating around, but they don't affect these kind of things. And it's not just the density profile. We're able to uncover scaling relationships for, say, abundances of voids, the number function or the volume distribution of voids, and for the ellipticities, using analytics and semi-analytics. So there's a fundamental connection between theory, which is n-body simulations, is telling us what the dark matter is doing, and observations, or at least mock observations. But here in these plots, actually, we've matched to real observations of voids using our simulations and our HOD model. There's a fundamental and deep connection between voids in theory and voids in data. Potentially just simple scaling relationships. That's a very powerful idea. We're still exploring it. But even if you don't believe that, if you don't think this whole scaling arguments work out, you can still extract useful information about voids. For example, here's a way of extracting a real space density profile out of a redshift survey, out of a redshift space survey, without doing any modeling and without any parameters. It's a simple idea. You take a void, and in an isotropic universe, voids have no preferred orientation. So I can take a bunch of voids and stack them together, align their centers, and it must be a sphere once I have enough voids. And it turns out enough means like 40 or 50 voids. I get a sphere. I can take that sphere and I can project it onto the plane of the sky. This immediately removes any line of sight distortions. So any peculiar velocity, any distortions due to, say, incorrect cosmological parameter modeling for constructing my coordinate system immediately get projected out by definition. And then I can de-project it back into a sphere, and I can recover, this is an example, again from simulations, but we've shown this in observations too. You can reconstruct the real space density profile without doing any modeling at all.
This is kind of related to the Alcock-Paczynski type of.
This is very related to Alcock-Paczynski. It's the same operation that we're going to do, except now we're squashing the line of sight dimension. But it's the same operation of stacking and constructing a sphere that I'll show later for Alcock-Paczynski. Yep. It's just geometry. That's all that is. Now, what about dynamics? Well, it turns out. Will this movie start?
Oh, you may need to move the mouse. Click on it. Actually, the mouse on the.
Okay, I need to do this, and then do this.
Oh, there we go. Oh, no, sorry.
Wait. Codec unavailable.
Sorry about that.
Okay, I want you to imagine this. What you're seeing are voids at very, very high redshift. These are almost like proto-voids, just the initial basins in the density field. And then slowly over time, you see this kind of percolation at high redshift, voids going in and out because it's really noisy. But eventually, voids stabilize, a basin forms, and it persists. So what we found, what we want to do with this project, with this paper, is construct void merger trees, where we take a void at redshift 0 and trace back its family tree, back at high redshift, to see, look at the amount of mergers, the amount of evolution, how much it moved. Turns out, voids don't have family trees, they have family sticks. A void that forms at high redshift just persists.
Don't they avoid each other? I mean, there's no attraction, right?
What voids will do, this movie would have shown you, is if I have two voids, at high redshift there is a mixing. Until around the scale factor of 0.3. There's mixing, there's merging, but eventually you get two basins, and the walls between them do slowly empty out, but they remain as two distinct basins. A larger parent void can be identified as the whole thing empties out. So we get a new void, but these two subvoids still persist. So if I look at the mean number of progenitors for voids that can exist at redshift 0, scale factor 1, it's just about 1. And then I run out of voids at high redshift because I'm creating voids with time.
So are you saying there is what in turbulent speak would be an inverse cascade of voids? A kind of in other words, a hierarchy, agglomeration would be building large structures from small ones.
Yes, and we call this annexation.
Same thing. I mean, so can you build a model of this like colloidal aggregation? You know, where you talk about basically you prescribe rules for interaction of two things, and then you two interact, and another one accretes it, and you end up. It's another way to say it, which sounds very much like this is bubble competition.
Mm-hmm. That's very interesting. There has, I'm vaguely recalling a paper that I think incorporates some of those kinds of ideas in order to predict a void abundance.
Yeah, but that's why you want to predict the void. You want to predict the void population as a function of scale, which is what those models do.
That's a very interesting idea. Yeah, I like it.
I have a question. If you take two voids, I would have thought they would have gotten bigger because that area is underdense, so it expands
They do.
faster.
The walls between them get thinner and slowly less dense as the galaxies stream out, and they collapse. The walls collapse and get thinner.
But the position you're saying, I would have thought they would have gone away from each other because that area being underdense been faster than the other.
But in an isotropic universe, it all balances out. Void centers, this is another thing we examined in this paper. I don't have a plot of it here. Void centers hardly move. Like less than...
At the very beginning, you showed this cosmological simulation, and everyone, your eye focuses on the overdensities getting more dense, but the underdensities, they're not moving. They're just getting more dense.
They're just getting bigger. Voids are so boring. I mean, we wrote a whole paper about it. It was remarkable how boring they were.
But does the volume of the voids increase?
Yes, it absolutely does. Yeah. Yep. But they don't die, and the centers don't move. All right, so let's do some cosmology. So we've developed some cool ideas, like voids persist, they're boring, they maintain this memory of the initial conditions. They actually don't have very much dynamical evolution. And there's these fundamental connections between theory and observations, between voids and dark matter and voids and galaxies. So perhaps our leading, most interesting project, I shouldn't say most interesting, the project that really has driven a lot of our own research into voids is the Alcock-Paczynski effect. Alcock-Paczynski effect or test tells you that if you have a set of standard spheres in the universe, you can measure cosmological parameters. Because you can measure the extent along the line of sight, and you can measure the angular extent. You take that ratio and you get a function that depends on omega matter, W naught, WA, all the rest. So all you need are a set of standard spheres. You can measure these extents along the line of sight as a function of redshift. This gives you what we call the stretch. And the value of this stretch as a function of redshift varies depending on the underlying cosmological parameters. So clusters are kind of round, right? You could use them for an Alcock-Paczynski test, except that peculiar motions are 200 times stronger than this effect. Well, what about voids? Well, voids are not round at all, but just like we had the trick we played, the game we played to get the real space density profile, voids in an isotropic universe, when stacked together, must be rounded. They must be spheres. And so we can do this. This is in data. This is in SDSS. Stack a bunch of voids together, and now you're looking at two-dimensional density profiles. You see the empty center, a steep wall, slightly overdense compensation. And we can measure the shape of this wall, build these stacks as a function of redshift, and get cosmological parameters. You can build essentially a Hubble diagram, and there's a stretch diagram as a function of redshift. Now, a couple years ago, Guillaume Leveau and Ben Wendell predicted, using simulations, using Fisher matrix forecasts, so all those caveats, predicted that if you take an upcoming galaxy survey like Euclid, which is going to capture around 1 million voids. And these surveys, which are designed to go after baryon acoustic oscillations and weak lensing, if instead you took the exact same survey and found voids, stacked voids, built a stretch diagram, and measured this Alcock-Paczynski effect, your constraints on W0 and WA improve by up to a factor of 10. That's through the sheer statistical weight of voids.
So is that adding it to BAO or just voids?
Just voids, plus Planck prior. All this is plus Planck and supernova. But just switching out BAO for voids. And it's through their sheer statistical weight. The BAO is a 150 megaparsec thing. There's only so many 150 megaparsec patches in the universe. But voids go all the way down to 5 megaparsec. You're probing smaller scales. So even though you lose a lot by having to stack, you still have a lot more voids in the universe than you have BAO features. So statistically, they outweigh the BAO. Now, there are systematics. There are still some residual systematics in voids. But here they are. If in the simulation, I turn on peculiar velocities, this is what happens to my Alcock-Paczynski measure. A uniform compression along the line of sight. It competes with the Alcock-Paczynski. It shrinks voids along the line of sight, but a constant factor across all redshifts. This is in dark matter. This is within a high-resolution n-body simulation. What about Mach galaxy populations? Well, here's dense Mach galaxies, sparse Mach galaxies, different redshifts. All these little bars represent all sorts of different stacks of voids at all sorts of different sizes. And same correction factor. If I measure voids in redshift space with peculiar velocities, and I multiply all of my stretch measurements by a factor of 16%, I get the expected signal.
Is that 16% and on the amplitude of peculiar velocities?
We don't know. We have no idea where this factor comes from. Presumably it depends on cosmology and the amplitude of peculiar velocities themselves. That's the next paper. That's the next thing we want. We want to understand the source of this. This was just verifying that even accounting for sparsity and bias, it's still a uniform factor. So when I go to data, when I go to voids in the SDSS, which is not an optimal survey for voids, relatively low redshift, relatively sparse, relatively very complicated survey geometry. So I don't expect that 10% or 10 times better than BAO, but applying the same correction factor that we get in the Machs to the data, we get a stretch diagram like this, where I've divided out the expected stretch of lambda CDM, so it's easier to see that correction factor. We can convert this into a likelihood on omega matter. It looks like that. It's around a 3.5 sigma detection of this Alcock-Paczynski effect. But that's with just 2,000 voids. The 2,000 voids that we have now, we have a detection of this effect. The next generation of surveys, Euclid, W first, will have 1 million voids. So this can only get better. This can only get better with more voids. And speaking of more voids, you can just count them and use them as a cosmological probe. We're able, once we account for sparsity and bias in survey geometries, we're able to match void abundances in surveys, real surveys, with Mach populations. Lambda CDM predictions. We see no disagreement. And you can, and we have some theoretical models, some analytic prescriptions for generating abundances of voids. That kind of sort of work. Not quite there yet, but give us at least an order of magnitude. And you can turn this into constraints. Just go around and start counting voids in your survey, and that can tell you about cosmological parameters. Another thing you can do is cross-correlate voids on the sky with the cosmic microwave background. This gives you the integrated Sachs-Wolf effect. A photon coming into a void has a different energy than a photon coming out. Really tiny effect for voids when you just have one void, but if you have 1,000 voids, this Planck collaboration did this, you get a cold spot. And they have a 3 sigma detection of this ISW effect in the Planck data with our void catalog, with our public void catalog. You can also cross-correlate with other galaxies and look for gravitational anti-lensing. So not anti-gravity lensing, but gravity anti-lensing. So instead of making Einstein rings and arcs around overdense structures, you have Einstein spokes. Galaxy shears will tend to align and point inwards towards the center of the void. Last year, Peter Melchior at Ohio State did this with the shear measurements of galaxies and our void catalog. After you get about 1,000 voids, you get a decrement in the shear signal. That's about what we expected from models of the profile. And then just a couple months ago, Bhuvanesh Jain and Joseph Clampett, like I mentioned earlier, did a slightly different approach, different way to maximize this kind of signal. And they're able to access the dark matter density inside of a void without relying on any scaling arguments or using galaxies as a tracer, just looking at the shear measurement. And we're starting to be able to get constraints, real observational constraints of, say, those profile parameters. And you can cross-correlate voids with galaxies or with matter. You can build a void model just like you can construct a halo model. And some interesting features emerge. Like if you construct the bias, which is the void matter power spectrum divided by the matter power autocorrelation function, just the bias, the relationship of voids to their environment. Small voids have positive bias. This means that small voids tend to live inside of larger overdense clumps. That's just how they are. They have very tall compensation regions. Large voids have negative bias. Large voids truly reject matter. They live inside of even larger underdense regions in the universe. You can only get this with voids. This is imprinted from the initial conditions. This is telling you that a center of a large void is not causally connected at large scales to the matter surrounding it. You can only get that from the initial condition, and you can only get this with voids. It means small voids positively biased, large voids negatively biased. It means there's a point where the bias is exactly 0, where the large scale power in the void matter cross correlation is identically 0. There is 0 large scale power. And if you run the clock backward, this is in simulations, to higher redshift, voids evolve, their environments evolve, these curves change from dotted to solid lines, but this pivot point stays fixed. A scale that stays fixed as a function of redshift is called a standard ruler. And a standard ruler appears in the void galaxy cross correlation because of this unique relationship imprinted from the initial conditions. I said earlier that voids are great places to study exotic dark energy because they're dark energy dominated. Here's an example of that. Again, this is from simulations, comparing lambda CDM to a model of dark energy that's coupled to dark matter, a coupled quintessence model. And the profiles change. You see a few sigma difference in the profile. They're emptier. You get a population of voids that's bigger than in lambda CDM. And it doesn't look like much, not very significant. But what we've done here is to construct a mock galaxy population and limit the volume in our simulation so that it matches the volume that we have in our current void catalogs. So this is telling you that today, with the void populations that we have observed already with our 2,000 voids, you can potentially put constraints on this coupled quintessence model. These simulations, these mocks, have identical, or nearly identical, 2-point power spectrum in the galaxy. You cannot tell the difference between lambda CDM and this exotic model just looking at, say, power spectrum. But you dig into the voids, where they've been dominated by dark energy for longer, they're probing more nonlinear scales or smaller scales, and they can give you access to this information. And if you're sick of cosmology, you can even do astrophysics with voids. Here's an example of that. If I put a high energy emitter, like a GeV or TeV blazar, behind a void, those photons will pass through the void. And if there is, these photons will spontaneously paraproduce because that's what they do. And they'll generate positrons and electrons. If there's a weak magnetic field in the void, then these positrons and electrons, their paths will curve, and they'll emit synchrotron emission. So if you look through a void to a high-energy emitter, a TeV blazar, you'll see the blazar itself. This is with something like Veritas or Fermi LAT. And you'll see it's surrounded by a halo. This will only occur if the void contains a weak magnetic field. I say weak because if there's no magnetic field, there's no synchrotron emission. And if the magnetic field is too strong, then the paths curve before you can generate this halo. So it probes, this halo will only exist if the magnetic field is between, say, 10 to the minus 18, 10 to the minus 12 gaps. The only way to get a magnetic field deep inside voids is to have it there since the very early universe. There's no known way for astrophysical generation mechanisms like dynamos and AGN or galactic winds to push magnetic flux deep into voids. They're energetically, they just don't have it. So if you look through a void at an emitter and you see this halo and you measure a magnetic field, that's a measurement of primordial magnetic field. The voids give you a window into the early universe, and this is one way that they do it. Because there hasn't been nonlinear processing inside of voids. It's all leftovers from the early universe.
Well, there has been some criticism to this mechanism based on the fact that the wire beam will relax quickly, put all the energy into thermal plasma. And you wouldn't see the beam electromagnetic cascade developed enough to be seen from Fermi in low energy gamma rays.
Right. So you're absolutely right. This isn't the only
the current
approach.
state. I mean, is it settled somehow? I saw
There's debate.
Still debate.
I won't comment on the debate because I don't have a particular dog in that fight. So there is debate about these kind of generation mechanisms, which is more important. See, observing a halo around a TeV emitter is not the only way to constrain magnetic fields in voids. You can look at spectra of AGN, and you can also just cross-correlate sources, positions on the sky, with voids themselves. And if there's a relationship there between source, position, and the amount of voidness between us and the emitter, that tells you something. It tells you something about the extragalactic background light, tells you about something about primordial magnetic fields. We're going to have a paper on that in hopefully a month or so. So all of this, we have detections of cosmological results. ISW, Alcock-Paczynski, Antillen, and that's with just 1,000 or 2,000 voids. But the next generation of surveys will have, like I said, 1 million voids. And so these constraints will turn into measurements. Or sorry, these detections will turn into measurements, will turn into constraints. We'll be able to access, we're doing more forecasts, more predictions with our better understanding of voids, with our understanding, like our links between theory and observables, these almost trivial relationships inside of voids. We're exploring all sorts of ways to use voids for cosmology and astrophysics. We're putting everything we know online at cosmicvoids.net, including our code, so that it's a repository for not just our projects and our ideas, but your ideas too, and your projects. If you can think of a way to extract useful information from voids for cosmology or astrophysics, we're trying to make it as easy as possible so you have as many tools as possible at your disposal to do that, to do it as quickly as possible. So I'd be happy to talk about any of these applications or any of our other ideas for the rest of the day. Thank you.
Any questions?
Okay, so have you done your analysis just on real data with no simulation stuff put into it?
So which analysis? So let me see. This is real data. No simulations here. This is a measurement. That's a measurement. That's a simulation. That's a measurement. That's in real data. Calibrated on simulations to get the bias. You're allowed to calibrate your estimate. Simulation, and I think all the other stuff is simulation. So we use simulations to understand void properties, to explore these kinds of links. But then we go out in real galaxy surveys and we get the job done.
What is the typical magnetic field in filaments?
In filaments, oh. Do you know? I think this is something that we don't really know. And I think it depends on if it's primordial or astrophysical generation mechanisms. Because if it's something like AG intergalactic winds, we're going to have a hard time magnetizing the filaments. If it's primordial and it's been there since forever, then
Same as in voids or fire? Should be compressed by...
if it's primordial, or if the astrophysical mechanisms generate early enough, it will be compressed. It'll be like 8 to the minus 2/3 or 3/2 or whatever the factor is for scale factor. It'll be much stronger than voids. And that's also if it's primordial. It'll be much stronger than voids. If it's magnetic fields are just locked up in clusters and in galaxies, if the generation mechanisms happen at too late of redshift, then it could be close to zero. It could be very similar to what's in voids. I think this is still an open question, theoretically, too.
I was going to ask about filaments, but from a simpler question. What is relation of filaments and voids? In other words, are filaments formed basically in interstitial regions of a bunch of voids?
Yes.
So
and voids also contain filaments.
I mean, they
inside.
should be at the vertices of the tessellation, basically.
Well, the clusters are the multi-dimensional, three-dimensional vertices.
Right.
And then there's two-dimensional vertices. I don't know if I got it. And then one-dimensional vertices. There's planes and filaments and clusters. All of them separate.
Have you thought about looking, the 150 megaparsec scale for DAO, but you have a new standard rule, let's say 28 megaparsecs. Have you looked at what that will do for dark energy and dark matter?
No, we haven't. We weren't actually expecting that to pop out. We were just looking at bias. This paper was going to be about looking at galaxy bias using voids to measure galaxy bias. That popped out. We're still fleshing out the details and the implications.
Does it look like it has any bad systematic errors? I mean, the good thing about DAO is there's not a lot of systematic errors for it.
Right.
Does that, when you were 18 years, does that look like it has or it doesn't have?
It has systematics in terms of sparsity and bias, just like the density profiles you have to rescale. If I look at a lower density population of galaxies, this whole thing shifts.
So the scaling, you have to get the scaling right to get that scale right. Is that right?
You have to, once you have a galaxy circle, and say it's uniform density as a function of redshift, so you've taken that into account. Then you compute the power spectrum of the galaxies, you find the voids, compute the power spectrum of the void galaxy cross-correlation. This, as long as your survey volume is big enough that you get the biggest voids, and as long as it's dense enough that you get some smaller voids, this will cross through zero somewhere. And if you do slices in redshift and that value changes as a function of redshift, that tells you about cosmology.
So it might be easier to do early dark energy with a smaller scale.
Mm-hmm.
Any other questions? Okay, let's thank Paul.
All right, grad students thing.
Suggestion for you.
Yeah.
You should label the very nice. And also the grad so actually, but you should label each slide whether it's a simulation or a measurement.
Oh yeah, I deliberately mixed them up. Just
Yeah, right, but if you put a label on them,